The concept of dark matter has been hypothesized for a number of years. The observed orbital speeds of stars around the galactic center of various galaxies is one of the reasons for the suggestion that dark matter exists. It's also been observed that the speeds of galaxies interacting with each other also suggests the existence of dark matter. The observation that the universe's expansion seems to be accelerating suggests an energy source responsible for this accelerating expansion. Acceleration requires a force to be applied, and a force being applied implies an energy source. This energy source was named dark energy. Many efforts have been made to determine exactly what dark matter and dark energy are. There have been a number of suggestions for dark matter, such as the WIMP, weakly interacting massive particle. There are others, but I do not want to belabor the point because that's not the purpose of this video. Similar searches for dark energy have resulted in astrophysicists making statements like, the use of the word dark only describes our ignorance about what is going on. Suffice it to say, all efforts to determine what dark matter and dark energy are have failed. In the history of physics, there was a time where something else was hypothesized to exist, where efforts to find this something else failed. This was the medium of light. At one time, light was suggested to be a wave, and waves require a medium for propagation. The medium was given a name. It was called ether, and the characteristics of that ether was determined by the characteristics of light. Efforts to discover the ether all failed. Finally, the Michelson and Morley experiment was done, and this suggested that no medium of light existed, and this resulted in the abandonment of the ether concept and the realization that light had a dual nature. Sometimes it acted like a particle. The photoelectric effect is an example. And sometimes it acts like a wave. Refraction, dispersion are also examples. Given what has happened historically with ether, I would like to explore the possibility that neither dark matter nor dark energy actually exists. This requires me to ask questions about what has to be changed in our present understanding of physics in order to explain observational evidence. This effort has been made in theories like the modified Newtonian dynamics, or MOND. In this approach, the basic premise is that high accelerations, like those present in the solar system, do not apply to the low accelerating environment present in galaxies. This results in gravitational forces being proportional to the square of the centripetal acceleration instead of being proportional to the centripetal acceleration. This is not the approach that I wish to explore. But my approach does look at the orbital speeds of stars about galactic center. Newtonian physics predicts that the stellar velocities about the galactic center will drop off as you look at stars with greater orbital radius. The observed velocities of stars do not drop off as predicted by theory, and this is illustrated in the graph that you see. The difference between the two lines in the graph is presently explained by the existence of dark matter. But I'm assuming that dark matter does not exist because all attempts to find it have failed. Orbital velocities are predicted by applying Newtonian physics. Of course, since Newtonian physics has been replaced by general relativity, ultimately, this discussion will have to be extended to general relativity. And that is beyond the scope of what I want to do here. So the gravitational force causing the orbital motion of stars is given by the equation that you're seeing on the screen now, where F is the gravitational force G is Newton's universal gravitational constant, the accepted value being 6.6743 times 10 to the negative 11 newtons meters squared per kilogram squared. M is the mass of the object producing the gravitational force, and m is the mass of the object experiencing the force. And r is the radius of orbit of the, in this case, orbiting star. This gravitational force produces a centripetal force, given by this equation, equation number 2, where v is the orbital velocity of the star about the galactic center. Equating these two equations gives us equation 3, which can be rearranged for velocity, giving us this equation 4. It is this equation 4 that suggests the predicted curve in the graph that you saw. Obviously, the values of v predicted by the equation are incorrect. As pointed out before, we must ask the question, what has to be changed in this equation 4 in order to explain the observational evidence? Velocities are given by measurements, and you cannot argue with the observations, only argue about the accuracy of them. Mass and radius are also given by measurements. The current thinking is that there is invisible dark matter whose nature is still undetermined. Therefore, the current argument questions the accuracy of the value of m, mass, in equation 4. It is argued that there is more mass, in other words, dark matter, present, which will cause the curve to drop down less quickly than what would be expected on the basis of visible mass only. But I'm assuming that dark matter does not exist. Therefore, one can only argue about the accuracy of the measurements of visible mass m and the radius of the orbit r in equation 4. This only leaves the proportionality value g, which throughout history has always been assumed to be a constant. In fact, it is really quite difficult to pin down a true value for g, as noted by a number of independent observers. My approach is to question the constant nature of the proportionality value g in equation 4. I intend to show that using observational data for the velocities of stars around the center of the Milky Way, one can explain the Milky Way's stellar velocity curve by assuming that the value of g varies with distance from the center of the galaxy. I will further show that by assuming that g varies, one can eliminate the need for dark energy. So let us get started. If we are to accept that g in equation 4 varies with the distance r, we can arrange equation 4 to get an equation that gives us the value of the gravitational value g versus distance r, as in equation 5. I am going to present you with data for stars orbiting the galactic center. The data will be their velocities and their distance from the galactic center. I will include in this data the data for the 8 planets in the solar system as well as Pluto. And they will be the first 9 entries in the data. I include them because any changes to the theory must apply not just to the Milky Way, but also to the planets and even to here on Earth, where we can actually measure the value of the gravitational value g. Here is the data that I'm using for this investigation. The first 2 columns, it's the actual data that I was downloaded off of the internet. The first column is the radius of orbit of the star in units of kiloparsecs, and the second column is the stellar velocity around the galactic center, and its measurement is in kilometers per second. Columns 3 and 4 is exactly the same data as in 1 and 2, except it's been converted to standard SI units of meters for the radius of the orbit and meters per second for the stellar velocity. Columns 5 and 6, I will have to explain where I get them or how I get them later on. But 5 is the mass inside the radius of orbit, and its units are kilograms, and the 6th column is the measured value of G, or calculated value of G, in newtons meters squared per kilogram squared. Taking this data, we can look at columns 3 and 4, the converted data to SI units, and we can plot the velocity versus the distance from the galactic center on a graph, producing our graph 2. The previous one was graph 1, and as you can see, graph 2 has a shape that is very similar to that of graph 1. In order to use equation 5 to calculate the needed values of G to explain the observed velocities, we need to know the mass of all matter interior to the orbit. For the solar system, of course, this is quite simple because most of the mass of the solar system is concentrated in the sun, and so we can just enter into column 5 for the first 9 entries the mass of the sun. The process for finding the mass of the galaxy interior to the orbit of a star is a bit more complex. We begin by considering the entire galaxy. It's estimated that it has a mass of 1.5 times 10 to the 12th solar masses. And since the accepted mass of the sun is 1.989 times 10 to the 30th kilograms, the mass of the galaxy would be simply the product of those two, equaling 2.98 times 10 to the 42nd kilograms, as indicated in equation 6. Of this mass, only 16% is visible matter, stars, gas, planets, that kind of stuff. The other 84% is thought to be dark matter, but we're assuming that dark matter does not exist. Therefore, the mass of the Milky Way is only 16% of what we calculated in equation 6. And this is shown in equation 7 here. So we have 4.77 times 10 to the 41st kilograms as the mass of the galaxy. The bulge of the Milky Way has an estimated mass of 2.0 times 10 to the 10th solar masses. And of this mass, again, 16% is visible, not dark matter. Therefore, the mass of the bulge of the Milky Way is 16% of the product 2 times 10 to the 10th times the mass of the sun, which gives us a mass of 6.36 times 10 to the 39th kilograms, as shown in equation 8. The bulge of the Milky Way has a diameter of approximately 10,000 light years. This means, making the appropriate conversions, the radius of the Milky Way's bulge is 4.63 times 10 to the 19th meters. This radius places the entire mass of the bulge inside the radius of the star's orbits for all of the stars presented in the table previously shown. The mass of the disk of the galaxy can be simply calculated by subtracting the mass of the bulge from the total mass of the galaxy, as shown in equation 11, giving us a result of 4.71 times 10 to the 41 kilograms. In order for us to calculate the mass inside the orbit of a star, we need to know the density of the disk of the galaxy. To do that means we need to know the volume of the disk. It can be calculated by using the formula for the volume of a disk, which comes from the equation for the volume of a cylinder. The volume of a cylinder is the area of the end of the cylinder times its height. Well, same thing for the disk. The area of the surface of the disk, pi r squared, times the thickness of the disk, as shown in equation 12, where T is the thickness of the disk. For the Milky Way, the thickness is 0.3 kiloparsecs, which converts to 9.26 times 10 to the 18th meters. The diameter of the disk is anywhere from 170,000 to 200,000 light years. If we use the midpoint, or the average of these two, 185,000 light years, we can calculate the radius of the disk, which turns out to be, in meters, 8.75 times 10 to the 20th meters. Substituting this information into equation 12, we can determine the volume of the disk at about 2.23 times 10 to the 61st cubic meters. But we must not forget that there's a hole in the disk where the bulge is. We can't count that mass inside the bulge twice. The radius of the bulge is 1.5 kiloparsecs, or 4.63 times 10 to the 19th meters. And so we can again use equation 12 to determine the volume of the portion of the disk that's inside the bulge. And so substituting into that equation and working it out gives us a volume of 6.23 times 10 to the 59th cubic meters, which is almost insignificant, but we won't ignore it. So if we subtract it from our previous calculation of the volume of the disk, we come out with a total volume of the disk of 2.22 times 10 to the 61st cubic meters.